So, you guys remember what we were doing last time? What did we talk about? This was, we're still in chapter 3. We spoke about delta x is small and x plus delta x is approximately equal to, what was the formula? Alright, this was basically the linear approximation form that we learned from Calculus 1, and we reminded ourselves what the formula was, and we used it to approximate the values of some numbers. Now we're going to move on into using this to approximate solutions to differential equations. So this is theorem 3.2 in your book, I believe. We use this to approximate solutions to ODEs at a given point. The method is called Euler's method. And in Euler's method, we're going to basically be using this formula to sort of inch our way towards the solution. And remember, we don't really care about the solution on a whole, like the general solution as a function. Sometimes it's very difficult to actually find that. So what we do is figure out where exactly we want to know the value that the solution gives, and then find that number. And that's often a lot more easier than finding the solution in general. So that's what we're going to do. So we did that and we approximated a lot of numbers. We also found that when delta x was very small, the smaller it gets, the better our approximation, and that's going to come up again. But we will go through the method. So, how do I describe this? So first we're going to consider an interval in which to work, where A is the initial x value, B is the final x value, we define delta x to be the size of the increments that we're taking, right? Which we're going to be approximating each step of the way by this guy. Which we call the step size. Or the subinterval length. So basically what's happening is we have an interval AB. We know the value of the function that we want to find at this point. And what we're going to do is we're going to break this up into pieces where each length is delta x, right? So what we're going to be doing is we're going to, we know it here. We're going to use this formula to figure out what is the value here. Then we use it again, what is the value here? Then we use it again, what is the value here? And so we step towards our solution piece by taking step sizes of delta x, and ultimately we want to know what is the value when x is this, right? And this will always be given, and we'll also mention how many steps we want you to use. But that's basically the idea. Can you give me a formula for delta x? B minus a over n. You take the length of the interval divided by the number of steps you want to take, and that's going to give you the length of each of the pieces. All right? Okay, so that's going to be an important formula. So eventually we're going to tell you, approximate the solution to this differential equation using 3 steps, right? Or using a step size of blah, in which case you put that here and solve for n, and you can continue that way. Right? Okay, so once we have that, then we can fill out a table. So here's how the method is going to work. It's basically a table method where we will be able to use these numbers in it and the given differential equation. This table is a very short one. Basically starts with the x value, then there's going to be the y value, then we're going to have the y prime value. So basically we're going to start at x equals a, then we're going to jump to a plus delta x, right, to get to the next point. Then we'll jump to a plus 2 delta x to take another step, and we'll keep continuing this process until we finally end up with b. Right? So we start at a and we keep taking steps to inch towards b. Right? Now, here I can put some value here, let's say b. This is given. You're going to be given an initial condition, or you'll be able to figure it out, right? So we know that y at the initial point is the value b, right? Then you'll take that a, that's where you're starting, that's your first x value. The corresponding y value you place here, right? Now for this guy, all you're going to do is take the x and y and plug into that formula for the differential equation, right? Y values into the given ODE. So I'm going to give you an ODE, and I'm also going to give you an initial condition, and I'm going to say, oh, B is prime up. I'm using B for something. Right? So I'm going to give you a differential equation, give you an initial condition, and I'm going to say I eventually want to get to here. The guy that shows up here, this is going to be the answer we want. Right? That's going to be our goal. I want to know what is the value of y at this point, right? Even though I don't know a formula for y, it doesn't matter. I can figure out the value for it. Now, where this formula comes into play is in the y column for every point after the initial point. Yes? Yes, you'll need to fill out everything. Eventually we'll have to fill out everything, yes. So now, the formula is used once in this column, right? This is where you use theorem 3.1 from this point and everywhere down, right? So basically what we want to do is, we know what the y value is here, but we want to take a step over and figure out what is the y value there. Then take another step, what is the y value there? Then take another step, what is the y value there? And how we figure out the y value is by using that formula. We're basically going to take the old y value from the previous step plus the derivative of the old y value times delta x. Right? So basically what you can think of this formula as saying is that to get some new y value, it's going to be approximately equal to the old one plus the derivative of the old one times delta x. Right? That's sort of the idea we're using. Right? And so we can use that formula here. So I know what the y is here. If I take a step over, what is the y there? I use that theorem, right? Then what am I going to do is I'm going to plug this x and this y into that guy. So plug in the new x and the new y. And then I keep repeating this process, right? But that's basically how you fill out the table. So the second column uses theorem 3.1, or was it 2? So it's really an iterative process where you keep running through this algorithm until you get to the point where you want to get, right? So this is how you fill out the table, and we're actually going to do an example, but it's good to actually know how to fill it out, right? So that when you do an example, it will make more sense, right? So here is going to end up being your y of b, which is going to be the guy that we want to find. So let me show an example of how this would look. There's an example of a question you might be asked to do. And the problems won't be much different from this. The only thing that will be different is probably the wording, and the function would be a lot messier than this one. But since we're learning it, let's start out easier. Also, I'm giving you some examples of how different ways they can say. They can say use 4 steps, use 4 subintervals, use n equals 4. These all mean the same thing, right? So it's basically telling you how to find your delta x, right? So we're given a differential equation. I want to know what is the solution for y at this point using this interval, right? And did I say what the initial is? I have to give you the initial condition. Now, we've actually solved this guy in class before, but let's actually run through the method to try to see how this works. So what's the first step? In this case, delta x would be what? 1 minus 0 over 4, b minus a over n, so it's a quarter. So if we're going from 0 to 1 and we want to take 4 steps, each step has to be step size a quarter, right? So I know in this table that I'm going to fill out, this is the x, this is the y, this is the y prime. I'm going to start at 0. I'm going to jump by step size of a quarter. So the next one is going to be 0.25. The next one is going to be 0.5. x1 is going to be 0.75. And finally, I'm going to end up when x equals 1. Right? And what I really want to do is find what is the y value when x equals 1. Right? That's what we're after. However, I know when x equals 0, what is the y value? It's just 1, right? That's based on my initial condition, right? So those are these two guys here. Did someone raise their hand? I felt like that. Okay. So I'm given a differential equation, initial condition. I'm told the number of step sizes. I use the step size to figure out the delta x. That's going to tell me how to get to from the initial point to the final point. My initial condition is filled out in the first two columns of the first row. Now, how do I fill it here? Use the given formula, right? So what's the formula that gives me my y prime? It's just y. Whatever the y value is, I'm just going to write down here. Right? So in this case, my y value is 1. It's okay. Now, how do I get to this y value? Right. I'm going to take the old y plus the old y prime times my delta x. Now my old y was what? 1 plus the old y prime is also 1 times my delta x, which is 0.25. It's a quarter. So what do I get here? 1.25. Right? So it means when my x value is 0.25, my y value is approximately 1.25. What is the slope at that point? 1.25, because the formula just says take the y value. And then I do it again, right? So now I'm going to do here, what's the old y value at this point? 1.25 plus the old y prime is another 1.25 times my delta x, which is 0.25. 1.25 plus 1.25 times 0.25. That would give us 1 point what? 56. Did it give you more decimal places?
Do you want all of them?
Give me 4. We'll usually also tell you how many decimal places to use, but for now, let's work with 4.
1.5625.
Okay. What goes here? Same thing, because the formula says it's the y value, 1.5625. We're going to do a more complicated example first. It's later, but for now, we're keeping it easy. How do I figure this guy out?
1.5625.
All right, take the old y, which is the guy just above you, 1.5625 plus the old y prime, 1.5625 times your delta x. What is that, roughly? 4 decimal places.
1.953.
1.953.
1.
Okay, which means this guy is 1.953. Okay, and what about here? Well, we have that 1.9531 plus 1.9531 times 0.25. And 2.4414. And so here we don't need, because this is the guy we were after. So y of 1 is approximately equal to 2.4414, right? Or since we worked in 4 decimal places, we really can be sure of about 3. So in general, I'd probably work with 1 more decimal place than you're required, 1 or 2, to sort of get things more accurate. But at the end of the day, that would be your approximation. What are you approximating? What? Here? Well, if that's different, the whole thing is going to be wrong.
No, it's right. It's right. It's right.
It's right?
Yeah.
Okay. All right. So, what were we approximating? As in the function. We actually solved this guy before. How did we solve a guy like that? Separation of variables. How do we separate the variables?
dy over y.
Integrate both sides. This is ln y equals x plus c. So this means your y is equal to c e to the x. Y of 0 equals 1 means 1 is equal to c e to the 0. This means c equals 1. And so your actual function that solves this is e to the x. So when I say approximate the y value when x equals 1, what am I actually approximating? E to the 1. Right? So basically, we want to know, so we wanted to approximate e to the 1, which is just e, which by the way is 2.71828. It's an irrational number, it's a very famous one. And we were off by like 0.3, but again, we only took 4 step sizes. And this function actually, e to the x actually changes really rapidly, so taking large step sizes will really get you far away from the answer. If I use smaller step sizes, I would get even closer to this, which if you're interested enough, you can try yourself. But basically, that's the idea. So the idea is, by using this method, I won't know exactly what the function is, but sometimes I don't care what the function is. I just want to know what value will it be at this point in the future. And this approximation with 4 steps tells me that will be the value, approximately. Any questions on this? Very important to know, guaranteed to be asked a problem like this on the final. Guaranteed, okay? So, if you have any questions, now's the time. We'll do another example and we'll see if there are more questions. Use Euler's method with 5 intervals. To solve y prime equals x over y, where y of 0 is equal to 2 at x equals 1, i.e. find y of 1, which they could say it that way. And this is b, find the exact solution. Which for the past couple of semesters, this is actually a typical thing to happen. Where in the final, they'll ask you to solve something using Euler's method that you can actually find some other way and you sort of compare the answers. figure out our delta x. How do we figure that out? Huh? It's 0 to 1. Right. Note the interval we're looking at here is actually 0 to 1. How do we know that?
So we're given y of 0.
We're given y of 0, right? 0 is the x value. And then I'm asked to figure out what is it at x equals 1. Remember, the interval is talking about the x values, right? That's a very important distinction, right? So the problem might not tell you the interval, but you should be able to read it and figure it out, right? Your initial condition, the x value is going to be the a. And where they're telling you to approximate it, that x value is the b. Right? This means your delta x is equal to 1 minus 0 over 5. Which means now and we have when x is 0, so 1/5 is like what, 0.2? So it means you just jump by 0.2. The next value will be 0.4. The next value will be 0.6. The next value will be 0.8. Then we'll end up with 1 finally. What goes here? 2. When x is 0, y is 2. So that was just given from the initial condition, right? So remember, this guy here, this is from initial condition. Right? Now what is y prime?
0.
How do you get 0? Right, so according to my formula which I was given, the derivative in this case is x divided by y. So in this case, it's just x over y equals 0 over 2, which is 0. Right? And now what am I going to do here?
2.0 times 0.2.
Right here we use that theorem, y old, y prime old times delta x. That's going to be 2 plus 0 times 0.2, which is just 2. Right? And what goes here?
0.2 over 2.
Right. According to this formula, my derivative is given by this divided by that. So it's 0.2 over 2, which is what? 0.1. Right? Now I go to the next step. What do I put here?
2 plus
The old y plus
0.1.
the old y prime, right, from the previous row, times my delta x. Right? And what's that? 2.02. And what goes over here?
1, 4, 5,
Right, the x divided by the y. So it's 0.4 divided by 2.02, which is, wait, 0.198. Here, old y plus old y prime times my delta x. This one is 2.0596. What goes here?
0.6.
All right, the x value divided by the y value, which is 0.2913. 2.13 here. The old y value, 2.0596 plus the old y prime value, 0.2913 times the delta x, which is 0.2. That's roughly 2.1178. So this one is just going to be the x divided by the y, because that's the formula. Which is 0.8 divided by 2.1178.
0.3777.
And this guy, old y plus the old y prime times delta x. And this is roughly 2.1933. So y of 1 is approximately 2.193. Any questions on the method? Like how to fill out the table? Is it clear? So remember, you start by plugging in the initial conditions. Right, so they're going to give you a differential equation and an initial condition. The guy in the brackets here is going to be your x. This guy out here is going to be your y. You just put those in. Your y prime is always computed using the formula that you're given. Right? So they're going to tell you the derivative is found this way. And whatever that formula says, you do that with the x and y's. Right? In this particular case, it was just x divided by y. So to fill out this column, I always took this divided by that. Right? If it was something else, I'd just do that formula. Right? To fill out the second column, I'm using that theorem that we did, the linear approximation. Take the old y value plus the old y prime value times the delta x. Right? And your delta x does not change, right? It's always the 0.2 that you're multiplying right here. And the rest of it is just, plugging your calculator, hope you punch in the right numbers, and you should get the right answer. Okay? Any questions? All right. How do you find the exact answer?
You just take OD,
Solve the ODE. How do you do that?
so it's dy y is equal to dxx.
dy dx equals x over y, which means you separate the variables by cross multiplying. So you have y dy equals x dx. Integrate both sides. This gives you y squared over 2 equals x squared over 2 plus c. If I could solve for the y squared would just be x squared plus c. Just multiply both sides by 2. 2c is c. It's a different constant. We'll solve for it later. And so I could actually solve for y. The thing is here, y would actually be the plus or minus square root. Would I take one over the other?
Oh, the plus or minus? I'll take the plus because we know the value is positive.
Right. Ignore the plus, ignore the minus, right? Take the positive one. And we took the positive one because of the initial value. I know my output was positive in the beginning. If I put a minus sign there, it would be negative, right? So since the initial condition is so if I get a plus or a minus, I'll take the plus because that would agree with my initial condition. And here we need to find the c because we want to get the exact answer. So now, since y of 0 equals 2. This means, how do I apply this fact?
So it's 2 is equal to square root of c.
Square root of 0 squared plus c. Right? So this means when the x value is 0, my y value is 2. So I plug that in. And I have that. I square both sides to get c equals 4. This means for my y, I can take the radical of x squared plus 4. Now, this means that my y of 1 is just radical 5, right? Which, if you plug that in your calculator, what would you get?
2.236.
2.236. So here we're off by like 0.1. Or if we rounded, we'd be off by 0.0. But as you can see, when we finished this, we had no idea what the function looked like, but we could still get really close to what value it should be the output, right? And in this case, the differential equation was separable, but it's not always separable. It could have been something that we couldn't solve any other way, but we could approximate what the output is at some point by using that method. And again, the smaller we make our delta x, the better our approximation would be. If I wasn't satisfied with that, I could just make delta x, cut it into 10 pieces instead of 5, and I would actually get closer to the actual answer. Any questions on this?
How would you know if you're satisfied if you didn't know, like, I mean, in this case, we knew what the equation was, but the idea is that you use this when you don't know the equation. How would you know how close you are?
Well, there are two options. Maybe, like in real life, you would actually know what it is at 2 points, and so you can use what you know about those 2 points to judge it, as well as the approximation would actually start to settle. Eventually, when you cut it into more delta x's, you realize the first 2 decimal places are always the same. So you know the first 2 are correct, right? And then you do it more, and then you realize, oh, the first 4 are now the same, right? So you can choose ahead of time, oh, I want to be correct up to 5 decimal places. And you just keep making more delta x's until you hit. The first 5 decimal places aren't moving. It's the guys afterwards that keep changing. So you know those at least are right. So you can do that. That sort of analysis you'll probably need for the Excel homeworks, but in like on an exam, we'll tell you just use this many this for delta x. Any questions on this?
We're all geniuses in this class.
Which is good. Makes my life easier. Oh yes, correct. I got everything correct. Now I want to modify this to work better. Better in the sense that we get a better approximation in a lot less steps. Right? So here, I mean, we're talking about 5 steps, 4 steps, but in actuality, when these problems really come up where you would need a technique like this, you might have to take hundreds of thousands of steps or hundreds of steps. And of course, you'd use a computer to do it, but sometimes the computer processing time way down the CPU, takes a long time to get any meaningful solutions. So getting a solution faster is often a priority, right? So what we can actually do is we can actually modify this method a little bit, which we're going to get to the modified Euler's method, which is what we're going to start now, but we're going to need a new equation before that. So we have that same idea, right, where at some point x, I knew the y value, and I have this tangent line at that point. I want to get to some point x plus delta x. Right? So this is the actual y value. This point would be our approximate y value. So the idea is, if you get close enough, the difference between these two won't be that large. But here's the idea of how we get to make this better. How about in the middle, we take a half step. X plus delta x over 2. And at that point, we do Euler's method again to get a second tangent line. What do you notice about that approximation to the actual value? It's actually a lot closer. In the same gap, I can get a better approximation, which means that this guy, if I use this guy, I would take less steps. So how do we actually put this into machinery? Basically, the idea is going to be the following. I don't remember. This is theorem 3.2. Theorem 3.2. It's very similar to 3.1, except the form is different. If delta x is small and we know f of x and f prime of x plus delta x over 2, then f of x plus delta x is approximately equal to f of x plus f prime of x plus delta x over 2 times delta x. Right? So the difference in this formula is this guy here. Because we're not using the slope of the original tangent line, we're using the slope of the tangent line at the half step point. Right? And using that tangent line will give us a better approximation in the same time length. So, which means I can take even less steps if I wanted to and still get a better approximation. Right? So cut down on our computing time. So this is just a modification to your linear approximation formula. Now the problem is, how are we going to figure out this guy? For our purposes, we can actually use theorem 3.1 to help us in the approximation of this guy, and we're going to see how that works now with a few examples. So just like before, we're gonna play around with this formula a little bit to approximate some random numbers, and then we will actually use it in a method, in a table form, not similar to what we just did with theorem 3.1. So. Approximate that, yes. Now remember, we actually did this using the previous formula, so we can even compare our answers that we got last time. Use theorem 3.2 to approximate it, so I want to use this guy. So here, we would take our x to be what? Our delta x to be what?
Just 25.
Delta x over 2 is... Alright, so x is 25. The change in x is 0.1. Change in x over 2. That divided by 2, which is about 0.05. Okay. What is the function I would take here? radical x, which means the derivative is 1 over 2 radical x. And so radical of 25.1 is actually just f of 25.1, which by theorem 3.2, this is approximately equal to f of 25 plus f prime of 25.05 times delta x, which is 0.1. Right? So here, this is x. Here, this is x plus delta x over 2. Here, this is your delta x. Now this guy's easy, we know that. But what is this, the derivative at this point? Right?
1/2 radical 25.2.
Right. But you see, this guy, if we don't know what the radical of 25.1 is, how are we going to know what the radical of 25.05 is? That's even worse, right? So what we actually do is we actually use theorem 3.1 to figure this guy out, and then we come back, right? So back to theorem 3.1. To figure out the prime of 25.05, which is really 1 over radical 2 of 25.05, we use theorem 3.1, the form that we were using before, the old one, right? So basically, just approximate. So we go back here. In the table, it would be less, jumping around. But if you're doing it by hand for a single point, for a single function, it's sort of, annoying. So now by theorem 3.1, radical of 25.05 is just f of 25.05, which is f of 25 plus f prime of 25 times my delta x in this case is 0.05. And so this would be f of 25 is 5. F prime of 25 is 1 over 2 times 1/10 times 0.05. And what's this? 5.005, right? This means by theorem 3.2, our radical of 25.1 is approximately equal to 25 plus f prime 25.05 times 1. F of 25 was 5 plus f prime of 25 is just 1 over 2 times the guy I just got there, 5.005 times 1. And what's that roughly?
Should be 5.00999.
Do you have more?
0015.
When we did this with theorem 3.1 last time, what was the answer we got? Last time we got 5.005. And the actual answer is 5.00999002. So, theorem 3.1, we were correct up to 2 decimal places. Using theorem 3.2, we were correct up to 1, 2, 3, 4, 5, 6, 7 decimal places. Right? So it actually, we took one step, and we ended up getting like 7 decimal place accuracy instead of 2. Right? So this method really gets the job done a lot better, a lot quicker. Right? Now, how do we put this in a table to take advantage of this machinery? I'll tell you now, so the table is going to be a lot more annoying. Almost twice as annoying. So usually what will happen is, if you're asked to use theorem 3.1, just use Euler's method, they'll usually ask you for 4 or 5 steps. They ask you to do this other guy I'm showing you, they'll ask you for 2. Because 1, it's a lot longer, and 2 is all you need, right? 2 steps here will be like 4 steps there, right? Because you can see here, the same amount of steps, I got a lot better accuracy. So we really don't need to go as far. Using this formula in Euler's method gives the so-called modified Euler's method. Okay. Do you have enough space here to describe how to fill this table? Delta x is found in the same way. To fill out the table, this is the process. You're going to have an x, you're going to have a y, you're going to have a y prime, just like before. But then you're going to have a couple more columns, right? You're going to have to figure out what happens at your half step, right? This x value for the half step we called x half. Then the corresponding y value we called y half. And at that point we're going to use that to figure out y prime of a half, which is the slope at the halfway step. Right? So again, we're given initial condition of y of a equals k or something like that, and we start out the same way, a, k. And then we do a of x and you continue this process so that how we figure out the x values won't change. And eventually we want to get to b. So we want to approximate y of b. So you start with the initial condition, and this is actually computed the same way. Use old x and old y in given y prime formula. for this guy, you just take a half step with what you get over there, right? So this is the x old plus delta x over 2, right? You just take the half step. Right? And that is filled out in the same way. To compute this, what do you do? Almost. Use theorem 3.1 with your delta x over 2. This was like that time when I went back and on the side I computed the derivative at the half step. I was really trying to figure out this guy. And so this is going to be the old y plus the old y prime times delta x over 2 instead of delta x. This point is use the x half and y half in the given y prime formula. And that's always how you fill out this one. And that's also always how you fill out this one, right? So anytime you see a derivative, use the given derivative formula, right? When you're finding out y prime, you use the x and y in the given formula. If you're finding out y of a half prime, use the x and a half and y half in the formula, right? So that's the easy part. Y half, you use theorem 3.1. That's where you have to like go to the side and figure something out to come back. Now to figure out the y's is where you use theorem 3.2. So what this is going to be the y old plus this derivative. Don't use this derivative, you want the derivative at the half step. So it's y half old prime times your delta x. And you repeat that formula, and eventually you will end up with y b. More often than these won't matter, right? Because this is what you want to approximate anyway. So it's a little more involved, but as I said, we'd be able to use less steps. So we should be able to get it done just as quickly and get just as good an answer, if not better. So the difference is there's a second table attached to it, right? Where you have to figure out the half steps for the x, the half step for the y, using Euler's formula with the delta x over 2. Then using the derivative formula with these two to find that, and then use that guy here. Right? So it will take a little bit of practice. Let's see what example today. Here I said 2 steps, but we won't lose. Maybe I'll say 3 steps so you can sort of see it. Use the modified Euler method to work out the same guy we did last time, to approximate solution to y prime equals x over y, y0 equals 2, and x equals 1. Using 2 subintervals would give us just as good an answer, but to like get you guys used to the steps, let's use 3. Yes.
We're just essentially kind of just doubling the amount of steps we take in the old method.
Yeah. Like one step here is worth 2 or more steps in the other one. Right? And we pay for that by a whole three more columns. Right? So we'll reduce the rows but increase the columns, and
So we're just kind of just making delta x smaller, essentially, right? Or the steps rather that would take an interval and make it do.
yeah. The delta, we're not really making delta x smaller, but the idea is to go from one point by delta x. Instead, now we're taking 2 steps. Yeah, we're 2-stepping our way there instead of 1-stepping our way there. And it turns out that we can go through less iterations and still get a better answer. So, do we have this copied down? So here, delta x equals let's use 0.33. Start at 0. Next one is 3. I think we're using 1/3, 2/3, and then 3/3. Get rid of this now, because I need more space. Okay, let's fill this out. What goes here? Alright, initial condition when x is 0, my y is 2. Alright. Here? 0, because I just take x over y. So this just becomes 0 over 2 equals 0. Now the x a half, how do I do that?
0 1/3 times.
1/3 divided by a half, which is 1/6, right? A half of 1/3, which is 1/6, which is, as a decimal?
0.16667.
Okay, let's use 0.167. And how do I get to the y half now? So remember, here is we use the regular Euler's method with delta x over 2. Use this guy. So this is y old plus y prime old, but this time I use delta x over 2. So this becomes 2 plus 0 times is 0.167, which is just 2. Then here, I'm going to find the derivative using these two guys. Again, just x over y. I'm following the same formula, but I'm using the half steps. So this is 0.167 divided by 2, which is what? 835. Now to get this y, I'm going to use theorem 3.2. So I'm going to take the y old plus the y half old prime times delta x. So it's the old y, which is 2, plus this y prime, the last one that I figured out, times my delta x, which is 0.33. And that gives us what?
2.027.
0, 0.
2.027555.
Okay, let's just do 4 decimal places. So that's 2.0276. All right. How do we get the y prime? Yes.
Sorry, for the first column, for the first row and the last column, you just put,
Plug in the same formula here, but instead of using x and y, I use x half, y half.
okay.
Right, but it's the same formula.
Okay.
Right, every time you're finding a derivative, you use the given formula. It just depends which x and y pair you're using. To find this one, you use this x and y pair. To find this one, you use this x and y. Right, but you're always going back, for the derivative, you're always going back to the formula.
For the x half, what did you do?
Do a half step. Right, so full step was 0.33. Divide that by 2 is 0.167. Right, so I take half a step, half a delta x. And that's always going to be the guy I'm using here. How do we find y prime at this point? X over y. This x over this y. So this is 0.33 divided by 2.0276, which is 276.1628. And x a half, well, it's going to be this plus delta x over 2 is going to be what? 0.33 plus 0.167. 0.496. Okay. So remember here, keep adding delta x over 2. Here, keep adding delta x. Here, use y prime formula with x and y. Here, use y prime formula with x half, y half. Sorry, that is actually here in the y half. Okay, now how do I find the y half? Well, I take the old y value, which is this, 2.0276 plus the old y prime value, which is here, 0.1628 times my delta x over 2, which is 0.167. And what's that? 2.0556, which means here I get 0.497 divided by 2.0556, which is going to be what?
24177.
How do I get this one? This.
So in y half, when you refer to old, instead of like in the first method, the old is the columns that precede it instead of the row above.
Yes, here I'm talking about the guys that came just before it did the roll. Yeah. So I'm doing here, I'm going to take this old y and this y prime in theorem 3.1, but I use delta x over 2 instead of delta x. This one,
The old y plus
old y, so this one comes from the guy above, 0276, plus the y prime I use here is not this one, it's that one. 2418 times delta x, which is 0.33. That's what.
nine
2.1076. Usually if this comes up in a final, you'd stop here. They rarely ask for more than 2 steps. So you'd be done here about really. For this column, I always use that y prime. And what's the y prime here? The x, 0.67, divided by the y, 2.1076, which is? What's the other decimal place? 0.3178 what?
976.
So let's use 0.3179. Okay. X a half is just going to be this plus 0.167. Zero point 4849. Y half. Are the numbers I'm going to use to find y half. Remember, this is the formula. What goes here?
2.107.
2.1076 plus
3.3.
0.3179 times
0.48.
no, delta x over 2.
Oh, sorry. 0.49. Oh, point.
Always has this value. So 0.167. All right? And you find that. 2.1.
Do you want the whole numbers? Then it says 0, 6, 8, 9.
2.160.
0, 6, 8, 9.
Let's use 7. What do we find here?
Is that x to half correct?
It's not.
Because 485 shouldn't be
It should be.
0.836.
It's point what?
836.
I got 0.664.
Shouldn't it be going up?
It should be going up.
Yeah.
Yeah. So it's 497 plus
836.
836.
0.836.
837.
438.
837.
Point 497. 0.827, no?
836.
Or is it because we rounded that one?
Yeah, we rounded that one.
Yeah, because this one was rounded, so okay. Plus point. Okay. Yeah, we rounded this, so it's off by here, but that's fine. So now what do we have here? finally, the guy we wanted to figure out, 0.387.
2.1084, or what's what you get? 2.0.
1084. What is
2.17. I guess I was.
This guy.
Yeah, around different. Yeah, it might be. So it's 2.107.
plus?
Plus
0.318.
Plus the guy we got over here. 0.387 times our delta x, which is 0.33.
2374.
2.2374.
2374.
So y down is approximately equal to 2.2374. What did we get the last time?
2.193.
2.193. This was using Euler's method. And the actual answer was?
2.2361.
2361. So you see here, these first two are the same. Those two weren't even the same. So this is modified. It's as you can see, it's a lot longer, and until you get some practice in it, it's sort of be confusing to figure out which x and y should have been plugging in at what time. But you just need to remember that the derivatives always come from the general formula that's given for the derivative. The difference is in this column you're using this x and y in the formula, and in this column you're using this x and y in the formula. To figure out this y, you're using Euler's the formula we got in 3.1, which is just the old y prime, except you use delta x over 2. Because you're doing the half step to figure out the derivative at the half step. When you get to the y, now you use theorem 3.2, right? That's the guy that had the derivative of x plus delta x over 2, and so that's why I used the derivative way over there. And you go through those steps. Usually you'll be asked for 2 steps, so you would have stopped right here. And these we don't care about. I think we'll end there for today, unless there are any questions. So we've actually completed chapter 3. So the homework for chapter 3 is due. Also, for this homework, you're going to also use the computer a lot. So I think the Excel homework should be due. So homeworks 2 and 5 due next time. So homework 2 and 5 due Wednesday. Two is just some basic Excel stuff, which it seems most people were okay with. So I guess if you have any trouble with that, we'll deal with that on Tuesday. I'll try to remember to bring a laptop so we can set up the projector if it's necessary. And then, okay, we'll deal with that. But for now, we'll end there. So chapter 3 complete. These 2 homeworks due on Wednesday. You can touch.